In this video, we are going to discuss conversion problems. This is something we'll do a lot in lab and a lot throughout the quarter. This will be one of those fundamental skills that we draw upon again and again and again as we layer different types of chemistry concepts on top of this basic applied algebra. So let's start by talking about what conversion factors are. It's basically just a term that defines one quantity in the units of another. So conversion factors are definitions, and we consider them to be exact numbers. So they can be included in a calculation, and the number of digits that the conversion factor has won't impact its significant figures. And so basically what we do is we take a quantity and we multiply it by the conversion factor to get a quantity in a new set of units. Here's an example of a conversion factor, that 2.21 pounds equals 1 kilogram. When multiplying it against an original quantity as a conversion factor, we can write them as fractions in one of two ways, with the 2.21 pounds on top and kilograms on the bottom, or kilograms on top and 2.21 pounds on the bottom. And which of these versions we use depends on what the original quantity units are. Sometimes our conversion factors won't be stated as an equality. Sometimes it'll be something you have to extract from a problem's context. If you see a sentence in a word problem that says that one tablet contains 500 milligrams of vitamin C, you're being told a conversion factor. It's being written out. And you can convert this into the equality, one tablet equals 500 milligrams of vitamin C. And so this word contains right here is really equals. One tablet equals 500 milligrams of vitamin C. And then from there, we can think of it as a fraction in one of two ways, like we did with our pounds and kilograms. So let's try this. A speed limit of I-5 through Seattle corridor is 60 mph, or miles per hour. What is this as a conversion factor written as an equality or a fraction? So mph is miles per hour. This per is a way of saying divided. So I can say that for every 60 miles, your car will need to travel as fast or fast enough that it can cover that distance in 1 hour. So this is our miles per hour written as an equality. I can also write this as, from just the way it's written, 60 miles per hour. As a conversion factor, I can also flip this and say that in 1 hour, I travel 60 miles. So these are 3 different ways to write this as a conversion factor. So this slide is intended to just show you a number of different types of conversion factors. We've got metric system, the US system, and the metric to US conversions. I'll ask you to memorize a few metric conversions that we'll use again and again and again through this quarter. But I won't ask you to memorize US conversions or metric to US conversions. I'll always give those to you if they're needed to solve a problem on an exam or on a quiz. The ones that I think are worth memorizing are milliliters, or metric system, milli, kilo, and centi. Let's take a closer look at the metric system, because we'll use metric conversions quite a bit in this class. The beautiful thing about the metric system is that prefixes are used in front of units to increase or decrease how large they are. So if we have a prefix like kilo in front of meter, make kilometer, that means instead of 1 meter, we're talking about 1,000 meters. And so these create really simple equalities that are conversion factors. So a kilometer is 1,000 meters, a kiloliter is 1,000 liters, a kilogram is 1,000 grams. So some prefixes make things larger. Kilo is 1,000, mega 100,000, then it goes giga, tera, and penta. Of these, the only one we're going to use significantly is going to be kilo, and I think this one is worth memorizing. For units or prefixes that make things smaller, we use a lot more. Chemistry is looking at little things, and so these are all units that we use. Deci is less common. It's really just 10 to the 10th place, so to 10 to the -1. Centi is 100th, milli 1,000th, micro 100,000th. And so the ones that we'll use the most are centi, milli, and micro. And beware, micro and milli look pretty similar. Let's think about milligrams. If we're talking about milligrams, it's a little m with a G. But if it's micro, it's mu, which looks a lot like a little m and G. So exercise some caution there. Nano and pico are used commonly, especially when describing bond lengths, but we won't use these frequently enough that they're worth memorizing. When we approach conversion problems, sometimes they're very straightforward in the lab. Like I need to convert milliliters to liters, and it's a simple calculation. But conversions are also used in solving more complicated problems, commonly word problems. And really, it comes down to being incorporated into a problem-solving strategy. And when we approach problems, especially word problems or conceptual problems that also have a math element to them, it's important to break down the problem into smaller pieces and develop a strategy before solving it. And this class is an applied algebra class, and it's an applied algebra class that has the goal of building and strengthening problem-solving skills, in my opinion. And so these are the problem-solving steps that I go through for any type of problem I'm faced with that I don't immediately know what to do. I always sort my information first and extract it out of the problem so that way it's easier to look at. I then make a strategy for figuring out how to get from the pieces of information I know to what I want to know. We'll talk about dimensional analysis here next. It's a great way to solve conversion problems for a strategy. Then I just follow my strategy and solve the problem and then double check the answer. So the real bulk of problem solving comes in your first two steps: sorting out your information and identifying what is given and what it is you're looking for, and then developing a strategy. These are our two main steps in problem solving. So that way when we're plugging things in our calculator, that's the easy part. So here's dimensional analysis. This is a way of solving conversion problems. In dimensional analysis, you might also see it called factor label method. You use the units as variables to help set up a strategy to solve the problem for the conversion, which can be really helpful. And this comes to how we take our equality conversion factors and we can write them as fractions. So that way, if we have a given unit and we multiply it by our desired unit and divide by our given unit, these two cancel out and give us just our desired unit. This makes, I think, a bit more sense when you just take a step back and look at it in terms of variables. So let's call our given unit X and our desired unit Y. If I had an equation that looked like this, X times Y divided by X, I would be able to cancel out my X values just by looking at this and say, well, yeah, that equals Y. And so when we have a conversion problem, what we're doing is we're taking X our given unit, we're multiplying it by a conversion factor, y divided by x, to get our desired unit y. If we multiply this all out, it equals this representation here. So our x's cancel, leaving us with y. And this is how we can set up problems to get to an answer that we want based on the units that we desire. So here we go. If we wanted to convert pounds to kilograms, if we knew we had 164 pounds, so this was my starting point, and I wanted to end up in units of kilograms, I would design my conversion factor to help me get there. So I know that 1 kilogram equals 2.2 pounds, and I can write that conversion factor as a fraction in 2 ways. Now, which way do I want to use? Well, if I'm starting with pounds, I want to have pounds on the bottom of my conversion factor. So that way, when I multiply this all out, my units can be thought of as being pounds, kilogram, divided by pounds, where these cancel, leaving me just with units of kilograms. So I'll choose this version of my conversion factor to multiply my starting piece of information by. I'll carry out this calculation in my calculator by dividing 164 by 2.20 in my calculator. And that gives me the number 74.5. And then I'll use the units of kilograms that are the result of multiplying and dividing out all the units in this equation. So let's look at a single step conversion. If you'd like, take a pause and try this on your own first. And I'll walk through this myself. So convert 3 quarts of ethanol into liters. My starting point here is my 3 quarts, and my end point, my goal, is units of liters. So I'll start with my 3.00 quarts. I know I need to multiply this by some conversion factor and get into units of liters. So even if I didn't see this conversion factor given right off the bat, I could figure out what conversion factor I needed to make this happen. I know I want to have units of liters, so my liters need to be on the top half of my conversion fraction. And I no longer want quarts for units. That needs to be at the bottom, so that way these both cancel out. So I need a conversion factor that equates quarts to liters. And I've been given one. Great. So I plug in this 1 liter up here. So that's a 1. And my 1.06 quarts down here, 1.06. And I plug this into my calculator and divide 3 by 1.06. And if you do that, as I'm doing right now, you're going to get 2.8301, and it keeps going. My initial piece of information that was given to me was 3.00. That's 3 significant figures, right? My conversion factors are exact. So if I have 3 sig figs to start out with, I'm going to report 3 sig figs in my final answer. So that'll be 2.83 liters. So I'd like to walk through problem solving step by step. And I'd like to do it with a typical difficult word problem. And go through this for each step of how I like to solve problems. So a doctor recommends to a family that they give their 22-pound child 75 milligrams of ibuprofen every 6 hours to reduce a fever. The family has a bottle of infant drops with a dosage of 50 milligrams per 1.25 milliliters. To measure the medicine, they can only find teaspoons used for baking. How many teaspoons of ibuprofen infant drops should the child receive every 6 hours? So immediately I see a ton of words, and that is a mental block for me personally and many people. So I like to pull out the information given and list it on the side. So that way it's easier to process and decide how to proceed. So the information that's given is the 75 milligrams that's needed. This is what we know, and this is the most important piece of this. What we want to know is the number of teaspoons that we need to give the child. So immediately I've identified my starting point and my end point. And if you can't identify where to start and where to end, then you won't really be able to develop a strategy. So that's always my first step. Then I recognize that I've been given a conversion factor that in 50 milligrams or 50 milligrams of medicine will be in 1.25 milliliters of the medicine. I've also been given some extra information that I'm going to write down. I'm not sure how to use it, that the kid is 22 pounds, that the dose needs to be every 6 hours. There might be more information than you need in a problem. And part of your job as a problem solver is to sift through that information and decide what is useful and what is not. And then it's important to recognize what you don't have. One of the pieces of information that's missing here, if I need to get to teaspoons, is how to convert between milliliters and teaspoons. Now, this is a conversion I can go look up, or possibly it would be given. Now that I have identified my important pieces of information, I like to develop a strategy. So I have my starting point written out, my 75 milligrams of ibuprofen, and the units that I want to end up in, my end point. And in between the two, I start by just writing some lines that'll represent conversion factors in the fraction format. And then I always start by putting my units that I know immediately into the denominator of my first conversion factor, because I know these need to cancel. And so I can set it there, and right away I'm on my way to creating a strategy without too much effort. I can then take teaspoons and put it right here on the top, because I know I need to end with that, and I don't want it to keep. Now that I have my milligrams and teaspoons in my conversion factors, I can look at what I know and see if any of these match. Immediately, when I see milligrams, I think of my milligram to milliliter conversion. So I know I can put milligrams into milliliters. And so I'll put my units here. That leaves me in units of milliliters, and I need to get to teaspoons. So if I can come up with a conversion factor that brings teaspoons and milliliters as an equality together, then I'll be able to complete this problem. So I set up my strategy just with my units. I need a conversion factor that goes from milligrams to milliliters, and I've got that. And I need a conversion factor that goes from teaspoons to milliliters, and I can look that up, and I can get that too. Now, from this point, once I have a strategy based on my units, I can go ahead and just plug in those conversion factors. So my 75 milligrams of ibuprofen will be multiplied by 1.25 milliliters divided by 50 milligrams. My units of milligrams then cancel. I can then multiply this by 1 teaspoon divided by 4.93 milliliters. Now my milliliters cancel, and I'm left with units of teaspoons. So now I plug into my calculator 75 times 1.25 divided by 50 times 1 divided by 4.93. And that gives me this value right here. Now, if I take all my units and multiply them together, I have milligrams times milliliters times teaspoons divided by milligrams times milliliters. My milliliters cancel, my milligrams cancel, leaving me with teaspoons. And that'll be my units. And this is a long number that came out of my calculator right here. To determine the significant figures, I have conversion factors that are exact numbers. And I have one inexact number that I started with, my 75 milligrams. This is 2 significant figures. So I'll apply my multiplication and division rule for significant figures, and I'll base it off of my inexact number. So I'll report the least sig figs, which is 2. So I want to report 2 significant figures, which would be this 0.38. So I'll report 0.38 teaspoons of ibuprofen. That would be hard to measure. And the last step, especially in a problem that I'm not super confident about, is to double check myself. One way to do that is to make sure that your units properly cancel out. And we made sure that that happened when we did our calculation. So that can help me feel a lot more confident. The other thing to do is to try to check on my answer and decide if it's reasonable or not. And that's kind of an open-ended question. But I can look at the magnitude, 0.38. So this is less than 1. Does that make sense? Well, 1 teaspoon is definitely larger than 1 milliliter. And the amount of milliliters that I have in my ibuprofen is larger than the milligrams, or the mass, the grams in ibuprofen. So I would expect the number of teaspoons to be smaller than the number of milligrams that I actually have. And sure enough, I've got a small number for my number of teaspoons. And so that can make me feel a lot more confident. So let's try another conversion problem example. You can pause this video here and try it on your own first, and I'll walk through the problem right now. So right now, I'm going to read this problem and try to find my starting point and my end point. It says to convert a 0.75 pints to ounces. So there's my starting point, and ounces are the units I want to end in. So I have a start and I have an end. And I've given several conversion factors, that 1 pint equals about 473 milliliters, and 1 ounce equals about 30 milliliters. And I'm going to try to do this with correct sig figs. So I'm going to start with my 0.75 pints. And I know I'm going to have to multiply it probably by at least 2. I can always erase and add another line if it ends up being 3 conversion factors. I want to end up in ounces. I'm immediately going to take these ounces and make them the units on the top of my last conversion factor. And I'm going to take these pints and make them the first units that I divide by in my first conversion factor down here. So that way I know that these will cancel out. Looking up at my 2 conversion factors, I only have one that has pints in it. So I'll use that first. 473.176 milliliters equals 1 pint. If I were to stop here and just multiply my 0.75 pints by my first conversion factor, I'd have units of milliliters. But I don't want milliliters in my answer. So I need to have milliliters at the bottom of my conversion factor that's second, so they cancel out. And I have a conversion factor that equates ounces and milliliters, which is great. So 1 ounce is 29.573 milliliters. Now I'm going to plug this all into my calculator and get an answer that is 12.000202. Well, I've got 2 significant figures to start with. So I'll report 2 significant figures at the end of my calculation. So I'll have 12 ounces. And that's how we walk through one of these multi-step conversion problems. Here is another conversion problem. This will be completed in a separate video, but give it a try on your own.